Most people see the incredible power of modern AI, the flawless images, the instant code. But what you don't see are the hidden vulnerabilities and the creative battle happening beneath the surface. We've condensed Stanford's hour-long Lecture 4 into a single, compelling story, exploring how AI systems are attacked and how entirely new ones are being built to generate the future. As AI takes on critical real-world roles, from web search to autonomous cars, a dangerous paradox emerges: the more powerful the model, the more vulnerable it becomes. This vulnerability creates a fundamental need for adversarial robustness. The threat is real. An attacker can cause a safety-critical system, like a self-driving car, to fail to detect a stop sign just by subtly manipulating an image. The core weapon in this attack is the adversarial example. An attacker takes an image, say, of a cat, and adds tiny, imperceptible modifications to its pixels. These changes are invisible to us, yet they are enough to fool the neural network into confidently predicting something completely wrong, like iguana. How is this possible? It's an optimization problem. Attackers define a loss function and use gradient descent to adjust the input pixels, forcing the model toward a target label. This works because neural networks operate in an incredibly high-dimensional space where even tiny changes across millions of pixels can cause a massive shift in prediction. Attacks come in many forms. Prompt injection manipulates a language model by inserting instructions that override its design. Data poisoning modifies training data to teach the model incorrect patterns. Even a backdoor attack can embed a hidden visual pattern into the dataset, which the model later associates with a misclassification. The defense involves techniques like adversarial training, teaching the model to classify these examples correctly, input sanitization, checking inputs for abnormal patterns, and red teaming. But while we defend, the AI world is simultaneously focused on a different, transformative challenge: creation. Beyond classification and defense, a huge area of AI today is generative models. These systems aren't designed to classify data. They aim to learn the underlying data distribution to create entirely new, realistic samples of images, video, text, and code. The early pioneers of this creative push were Generative Adversarial Networks, or GANs. Imagine a fierce competition. A generator creates synthetic data, while a discriminator acts as a critic, trying to distinguish the real from the fake. Both networks train simultaneously, constantly improving until the generator can perfectly fool the critic. But this simultaneous training is notoriously unstable, often leading to mode collapse, where the generator only produces a limited variety of outputs. The new champion of generation is the diffusion model. This approach tackles image creation in two steps. First, it gradually adds noise to a real image until it's completely random. Then, the model is trained to reverse this process, learning how to reconstruct the image by predicting and removing the noise step by step. Because the added noise is known during training, the process is self-supervised. To make this computationally efficient, researchers developed latent diffusion models, which compress the image into a smaller, lower-dimensional space for the denoising process. These models offer precise creative control through conditioning. By converting a text prompt, like a majestic space cat, into a vector, the prompt can be combined with the image representation to guide the generation. This same logic is extended to video generation by adding a temporal dimension, ensuring consistency between sequences of generated frames. Generative models are now powering applications across super-resolution, image editing, and synthetic data creation, proving that AI is as much a tool for creation as it is for analysis. From the hidden dangers of adversarial attacks to the stunning potential of generative AI,